Good afternoon, everyone. Thank you for joining us today. For our next session, we'll be diving into machine learning with the talk title, Accelerated Machine Learning, Serving with Distributed Caches. Our speaker for the next session is Yaroslav. He's a talented software engineer with almost 3 years of experience in data and machine learning. His expertise extend across various domains such as computational biology, deep learning, as well as backend engineering. Please join me in welcoming Yaroslav to the stage.
Thank you. Hello, my name is Yaroslav. Today I'll be talking about accelerated machine learning serving with distributed caches. But first, let me introduce myself. I'm a machine learning engineer, and I've been working for TikTok for 1.5 years. And as far, I'm more like a typical ML engineer, whereas I just was called talented. Thank you. But I'm here today to hopefully improve my communication a little bit and maybe become a machine learning team lead, according to this classification on the right. So what I actually do at my job is I build and support production machine learning platforms. Those systems might get much more complicated than the system on the slide, but this is kind of a simple architecture for such a system. And what it allows to do and what it aims to do is to partially or fully automate some of the things that machine learning lifecycle includes. So those are data preparation, experiments with the models, and prototyping on different kinds of models and data pipelines. It includes model and data versioning. As you can imagine, if many data scientists work to solve the same problem, they can have different pipelines and different notebook services, different kinds of environments and code, and that can lead to certain problems. When something breaks, it's a bit difficult to backtrack the issues. So those systems aim to partially solve this issue by versioning every step data scientists take to experiment on their models. The next step is model evaluation. Before putting models in production, we want to verify that models performing well and the data actually can be loaded efficiently and fast enough into the models to perform well for certain use cases. And the next step is actual model deployment. And that can be complicated as well because model evaluation, model experiments, and model deployment can be done in different environments. And we want to experiment fast and evaluate models fast because we want fast iteration because machine learning is highly experimental. And we want to ease a lot of restrictions that are happening in production environments. But because of that difference, sometimes things can go wrong because of different environments in production and in testing. And those ML platforms try to remove as much as possible this discrepancy between model production environment and model experiment environment. And of course, those systems include different kinds of alarms, monitoring dashboards, and so on to check the performance of the model and maybe trigger some model retraining or other actions, or just notify some people that something is going on and maybe the model is not performing that well under high load or something like that. So today, I want to talk about machine learning for risk management and some use cases for that. I want to talk about production components. How do we put machine learning models for risk management in production and what problems we can encounter. And when the scale is big, we may want to save some resources when serving those models, or we may encounter problems with latency because we don't have that vast amount of resources to serve these models. And that's where I want to talk about caches and how caching for such models can help. So let's first think about a familiar example, machine learning in credit scoring. So for example, you request a loan in a bank, and what bank does, it will collect data from multiple origins, as depicted on the slide, and it will compute some risk score, and based on this risk score, it will offer you different terms, or maybe reject or accept your loan request. And the same thing can happen in social media in different ways. So there are a lot of risky behaviors that accounts in social media platforms can take, and some of them are kind of similar to credit scoring in banks. So let's imagine that there is a lot of parties that try to abuse the platform, and they use different tools to register a lot of accounts that maybe cooperate, or they may cooperate together to achieve like a certain result. Maybe they want to promote like a cryptocurrency scam or something like that, and they may engage in commenting and discussing that cryptocurrency course in the comments, that it looks legit to the user because they interact with each other, and they one of the accounts would ask how to get rich under like a video about personal finance, and the other would reply, oh, I got rich using this cryptocurrency course. I just learned how cryptocurrency works, and now I recommend it to everyone, so you're welcome, something like that. And the problem with that is that we have a lot more traffic and more risky scenarios compared to banks. And we often have to reply fast, because when you go to a bank and ask for a loan, you are probably fine to wait a couple of days until the bank processes your request. Whereas when you use a social media platform, you are going to be really frustrated if every action you take takes a lot of time to load the next page and verify that your action is legit and your account is legit. So how do we put it in production? That's the question. How do we put the same kinds of models in production for social media? Some of the use cases in identifying and assessing risks in social media environments are here on this slide. For example, maybe when some account changes its behavior a lot, we may suspect that this account is stolen, and we may use a machine learning to suspect that an account is stolen. But after that, we may want to decide what to do with that information. Maybe we should log off this user and ask for a one-time password next time the user is logged in. And maybe that can prevent a stolen account. Maybe we can notify the user using their email that their account was temporarily suspended because there was some issue and they need to verify their identity. Or maybe we can suspect that this certain account is a bot, and we may show CAPTCHA to prevent it from taking automated actions on the platform. So there are challenges to put those models in production, and the challenges are mostly related not to the model, because the models that run in real time should be fast, so they are pretty light usually, and the most prominent source of latency in production is actually not related to the model itself, but to data pipelines that are used to bring the data from users to the machine learning model. And compared to research or model training, data becomes more of a problem in production environment because it changes a lot, and it takes a lot of time to process it because we don't have it in advance, and we have to reply fast to the requests that users make. And moreover, there are a lot more components in production than machine learning code. Machine learning code is this black box in the middle, so it occupies not a lot of space in the whole production environment, and this is a challenge to optimize data pipelines sufficiently that this machine learning code can perform well and the whole pipeline can perform well. And the other problem is that serving infrastructure sometimes requires specific hardware, such as GPUs, which is harder to get, harder to scale, and it's more expensive to scale compared to CPU machines. So those two problems, lack of resources and data pipeline latency, make it hard to scale such models to really high amount of requests. So the question is, can we use some cheap resources, scalable resources and frameworks to achieve good results without using a lot of expensive hardware or running a lot of computation? So let's look at a real-time pipeline and components it can have inside. So it can have multiple components. First of them is an inference server, which handles all of the requests that need to perform some machine learning computation. It can host multiple models using multiple frameworks, and can forward the requests from users to the machine learning hosting device to perform machine learning computation. But before it does it, it needs to obtain machine learning model inputs from a feature store. And the feature store, it handles different kinds of data and data preprocessing. So those two components are very important to the whole optimization process and the whole real-time pipeline efficiency. So the problems with those kind of pipelines are, as I mentioned, we need to achieve low latency. And because of that, there can be a lot of timeouts, which lead to discarded computations, because an inference server can forward the request to a machine learning model, but the request times out, and that computation is no longer needed, but we just occupied a resource that we don't have a lot of. And the other problem is that offline feature retrieval is slow. So when we need to retrieve a lot of features from a feature store, some of them can be obtained with a lot of latency, even compared to machine learning model inference. So maybe getting the feature from the storage is actually takes more time than computing the result with a machine learning model. And using efficient memory storage to retrieve features fast is also expensive, and it uses a lot of memory, which is more expensive than cold storage. So the other problem is duplicated or almost duplicated requests. So you can imagine that users can take a lot of actions. In 1 hour, one user can leave a lot of likes on their videos or leave a lot of comments. And if we verify every request users make, then we can quickly run out of resources because we make duplicated, we compute duplicated requests a lot, because that's the source of the traffic is just like that. So this is the main problem that we want to focus on and try to solve, because all of other problems are kind of more difficult to solve and just require more kind of resources to fix them. So let's focus more on the components that we had in the previous slide. So Feature Store is a service that that unites different data transformations, so data storage, and a service for data scientists to discover and make new features from raw data. So it actually helps to unify certain pipelines for model training and models in production, because as you can imagine, when you train a model, you may use one pipeline to preprocess the data, but in production environment, you may forget to update the older pipeline, or you may use a completely different pipeline written in like another language or something like that, and it can lead to errors when deploying a model. And this service tries to solve this problem, but still data scientists may want to use some features that are stored in the cold storage, and we can't keep all the features in the fast memory. So we want to reduce our requests to this feature store as much as possible when we answering duplicated requests. So the other component is an inference service, and that service aims to solve the problem with machine learning model management and device management for running the machine learning computation. And it provides a lot of things out of the box for different utility things like metrics, alerts, monitoring, loading, offloading different models, and optimized runtimes for different kinds of framework. So we want to use this kind of software to use all those features and not develop them by ourselves as much as possible, because it's just simpler to use specified software. So duplicated requests, how can we solve that issue? We can have a look at caches, and caches are used for exactly that purpose in many different kinds of ways. So from CPU to distributed systems, caches are used to reduce the number of requests to slow hardware and use small amount of high performance resources to reduce latency in overall pipeline. So, for example, Redis is a distributed database which stores data in fast memory, and querying Redis is much faster than querying an SQL database. And this services are used to speed up SQL database queries in a way that you first query data from the fast memory, but the fast memory has less space available to it, so it doesn't fit all the data. If you find that your request data in the fast memory, then you obtain the results faster. If not, then you query the database as usual. So what we can do with machine learning serving services is actually the same thing as with SQL databases. We can store requests in request results in Redis database or in some other cache system. And if we don't find the result in the cache, we query the machine learning serving service and compute the result. So this is how that whole system changes when we add caches to it. It gets a new component called cache, and before fetching features and before running the computation, the inference service would check if the result for this request is already in cache. And for that, it will use some hash based on request features. So, for example, it can use user ID and the model name that this event wants to compute on. And when it misses the cache, it will compute the features and request the features from the feature store and send them to the machine learning frameworks to do the computation. So it actually allows us to share cache between different models and different use cases. For example, if we verify that some of the requests on the platform were allowed for a certain account, maybe other types of requests are no longer need verification because they are not that risky as the previous one, and the previous one was already allowed before. Yeah, that's really cool because caches are really fast and much faster than machine learning computation or getting the features from feature storage. And we removed two steps where we need a lot of computation and a lot of latency come from those steps. But we used more simple technology to utilize more simple resources because caches just need some CPU and memory resources, which are usually more abundant than GPUs and specific devices for machine learning. So for caches, we can actually use different kinds of software. For example, we can use local caches, which are hosted on the same machine as the machine learning models, or we can use distributed caches such as Redis. And distributed caches have a lot of advantages because they provide, usually that software provides a lot of utility things out of the box, such as metrics and decoupling, scaling, and things like that. So the big thing here is decoupling, because when you restart your serving service, you don't lose the data in the cache. Whereas if you use local cache, all the data would be lost when the service restarts, and the cache needs to warm up after restart. When you use a different service, you decouple those concerns, and you no longer need to warm up cache after your inference service restarts. Both of the methods are pretty fast, and local cache can be a little bit faster than distributed cache, but usually not as much faster, and distributed cache advantages can be a good trade-off to make here. This is an example of local with distributed cache performance from how to build a distributed inference cache with NVIDIA Triton and Redis. So that's a paper based on the same idea to use caches for caching some machine learning features for the models and caching the results. And you can see that there is not a lot of difference between local and distributed cache, whereas there is a lot of difference between no cache and some cache. And here you can see on the left that's nanoseconds. So when you use Redis, for example, you may get the result in couple of milliseconds, which is faster than serving any machine learning model. And most of it comes from network latency and not from something else, some compute. So that's just like a network call. The next problem with caches is that we have a lot of data coming into the service, and we cannot store all the data in memory even if the memory is cheap enough, we still need a lot of resources to save millions of requests. But what we can do with it, we can compress caches using some threshold. We say that after we make an inference for the first time for that request, we can store this request in the full cache if the risk is high for this request. So high risk means model score is high, higher than threshold. And if the risk is low, we just save this request in the request list. We do that to keep track of requests that already have been made, and we want to distinguish them with the new requests coming from the new users or new scenarios. And for user request list, we can use a Bloom filter, which is a binary data structure which can answer the question: is a member, is this member in a set or not? And it answers totally no or probably yes, because it can make mistakes, and but those mistakes can be controlled. The error rate for mistakes can be controlled based on the size of this structure, and it is highly memory efficient. So for 1% error rate, you need 10 bits per item. For 0.01, you need 20 bits, which is at least 10 times less memory compared to usual Redis cache. We discussed today how caches can increase performance and efficiency for machine learning serving. We discussed how multiple inference servers can share the same cache, and they can share the same cache between multiple models to build a hierarchy of events and hierarchy of risk. We can compress those caches to save resources and use efficient data structures to store the request list and the scores for high-risk events. And what we need to design for caches is an efficient hashing mechanism to hash the requests, and we need to control an eviction policy to allow high hit rate, because if the hit rate goes too low, it increases load on the serving services and feature storages, which we don't want to have because it increases the whole latency. So with different knobs, we can control and balance hit rate, resources, and false predictions. So we want to build some monitoring things for that system to additionally control cache hit rate and cache memory usage and the number of evictions in the past few minutes or something like that. So yeah, with that, my presentation is finished. So if you have any questions, you can reach out on LinkedIn, and I'll be happy to answer them. And yeah, that's it, I guess.
Thank you, Rislav, for your valuable insights. Thank you, everyone, for joining us today at Data Science Festival May Day. I hope you had an amazing time today. If you enjoyed the day, you can enter the ballot for Oktoberfest, which will be held on October 19 later this year. And please join us for networking and drinks at Spacebar downstairs. And at the end, I would like to extend a huge thank you to all our speakers, volunteers, our AV team, as well as our speakers, for making this incredible day happen. Thank you so much, everyone.